Hello everyone, I'm making this video just to show you that we can use programming to solve chemical engineering problem. And the computer programming language that I'm going to use is called Julia. And Julia itself is a programming language which is considered as high-level language like Python. However, the calculation using Julia is much faster than Python. It can be Someone would say that Julia can calculate as fast as a C or C++. So let's try to use Julia. My computer already has Julia installed, and I'm sure that you can find how to install Julia in the internet somewhere else. So let me show you the feature. So if I call the Julia command, or Julia, this is called Julia REPL, you can type in the code in this REPL, but it is not very beautiful here. I'm going to use another platform called Pluto, which is a web-based platform. I'm going to call Pluto and enter to load Pluto. Of course, you need to install Pluto separately. If you prefer, you can use some other notebooks like Jupyter or even Visual Studio for Microsoft to use Julia as well. You just have to tie Julia engine to that notebook. So once I import Pluto, I can call pluto.run just to call the browser. My browser, by default browser, will be called, and then it will run Pluto. This is what Pluto looks like. Okay. When you start, you can just click here to get a new notebook. This is what we have for Pluto. Basically, there's a cell that you can enter a command. Once you execute the command, the result will be shown up here above the cell. Okay, I'm going to show you in a minute. Let's switch to the problem that I'm going to show you for today in this video. The problem is the basic mass balance. Okay, in the problem, we have a stream of mixture of A and B feed into a process. And in this picture, you can see that the location highlighted in blue, location 1, 2, and 3, we don't have information yet, but we can find it out using simple mass balance. So let's try to work on problem first. If I say that the mass flow rate at this position 1, is M1, and mass fraction of A in the stream at location 1 is called X1. Similarly, we can assign M2, X2, and M3, X3 here. Okay? Now, we can set up mass balance around this system, and I'm going to write it down in pink. So for overall mass balance, you can get input basic mass balance is that in minus out equal to accumulation. And if we consider steady state, this accumulation term will be 0. For the pink system, the input is 100 minus output, which is 2 streams. First stream is 40 kilogram per hour, and then another stream is M1, equal to 0 at steady state. This is overall mass balance. The other balance that you can do is component balance of A. So in the same manner, input of A to the pink box is basically 0.5 mole fraction of A multiplied by the flow rate 100 subtracted by 0.9 times 40 of the stream up here. This is 40 plus X1 M1 equal to 0. This is component balance of A. around the pink system. We can do the same thing for this junction. If you take the mass balance, overall mass balance around the junction, you get M1 as an input plus 30, which is another input here. This is also considered as input, minus output, which is M2, equal to 0 as steady state. Similarly, if you write down the mass balance for A, species A, around the blue junction, you can get X1, M1, plus 0.3 times 30 minus X2, M2 equal to 0. That's overall and component balance around the blue system, blue junction. Now, if I write down another balance around this purple box, okay, as overall mass balance, you get M2, which is input, and we have two outputs. First one is 30 here, 30 kilogram per hour as an output, and the other one is M3 equal to 0, and then write down the component balance, X2, M2, subtracted by 30 times concentration of 0.6 here, so 0.6 times 30 plus X3, M3 equal to 0. Okay? You will notice that we have 6 equations. Within these 6 equations, we have 6 unknowns. The unknown that we don't know yet is M1, M2, M3, X1, X2, and X3. Total of 6 variables or 6 unknowns. Since we have 6 equations, that means we can find exact solution for this system of equations. Okay? What we are going to do is plug all these 6 equations into a solver and then let it run and find the solution for you. That will be really, really convenient. This is how it works. Within the Julia language, let's say this is Julia, we have to call a library that can have some ability to do the task that we want. The library that we are going to call, this one, is called NLsolve. It's standing for nonlinear solver. Okay? In order to solve this set of equations, we need to define the equation somewhere. So let's have equation ready somewhere, and this is what we call a function. So we are going to have a set of equations defined. The solver would need the initial guess as the initial number for solving these equations. So the problem or the engine would send this initial guess to this function to calculate whatever we have as an equation and then send back the error so that the NLsolve can do adjustment. After repeatedly adjusting the value back and forth, eventually it will give you the solution. Okay, this is the idea. The command that we are going to use is like this. NLsolve and name of the function following by guess value or initial guess value. Okay, we are going to do that. In order to use this library, you need to introduce the library to Julia. So the way to do it, let's switch back to my Pluto here. The way to call the library is to use the keyword using. I'm going to call NLsolve. Once you finish typing, you can hit Control Enter. The engine would execute the command. In this case, it would load up this library, and then at the same time, new cell would appear. If you hit Control Enter, new cell would appear. If you don't want new cell to appear, you can just hit Shift Enter. Okay? So if I call my function as function f, f is the name of the function. Eventually, I'm going to use NLsolve to call out this function. So therefore, I need to create the function first. In order to do so, we are going to use the command function. Please notice that every time we finish the keyword, the color of the word is changed. So this is the command, is known command for Julia. Okay? The command is function to create function. If I call the function as f, this is the name of the function that I'm going to create, followed by the list of variables. This list of variables, if I go back to this picture, the variable that will be sent back and forth from NLsolve to our function. Right now, I'm going to use the name x. Okay. Since we have 6 unknowns in our set of equations, all of these 6 unknowns must be named as x. All right. So I'm going to tell the engine or Julia that I'm going to create a function called f. And this function would receive or send variables by the name x. Okay. If you hit enter without control or without shift, the new line will appear within the cell. So we have not executed the command yet. We just enter the new line. So eventually, in your function, to solve this problem, you need to declare the equations within the bracket like this. Since we have 6 equations, let me go back to equation. The default for NLsolve is that your function must be equal to 0 on the right-hand side, just like what we just wrote in this slide. Okay, so I just have to copy everything here into the definition of my function f. Okay, so let's do that. So let's start with the first one, 100. I put 100.0 just to tell Julia that this number is a real number, not integer. Okay, whenever you put decimal point, Julia would consider it as a real number. 40 plus M1. Right now, I just use M1 as our notation. We are more familiar with M1, M2, M3, and so on. Once you finish this is the left-hand side of the equation. The right-hand side, for the right-hand side, the function or the NLsolve would assume it to be 0. So you don't need to write it down. So just write down the left-hand side of the equation. The next equation would be enter after you put comma in there. Okay, you can put equation, the follow equation from this point, or you can hit enter again to enter the new line. It doesn't matter for Julia as long as it is within the bracket. So the next one will be 0.5 times 100 subtracted by, I'm going to put parentheses, within parentheses, okay? 0.9 times 40 plus x1 times m1. This is the second equation. You can also notice that sometimes I put space here, sometimes I don't. It doesn't matter, okay? It doesn't matter at all. This space can be there just for our own eyes, so it would be clear for us to read, or you can put them together, closer together. That's totally up to you. So the second equation is enter, you have to follow by comma. Then I will complete these equations. There. Those are 6 equations that we are going to solve simultaneously. Okay. After you're done, all 6 equations in the brackets, you can put n just to say that this is the end of the function. Okay. Before executing, wait a minute, you have to make sure that the program understand or know the variables. Right now we use variable m1, m2, m3, x1, x2, x3. But these variables is not known by the computer. The computer assumes that the function must be sent by the name x. So we need to introduce whatever we put into the equation into the same notation as the computer understands. Okay, so we are going to assign m1 to be x number 1. Within the bracket here, that means this is called x as an array, but this is array number 1. Okay, repeat the process so that all the 6 variables will be introduced. All right. Also notice that this x and x1 here are not the same. Julia would consider this x as a variable, and x1 would be another different variable. Okay. So once you're done, you can hit Control Enter just to tell the program that this is what we just defined. So the program, after it's run, it will say that this is the function defined, already defined, and call f. Okay. Now, once we define the function, it is now ready to be solved. So in order to solve, just like what I wrote here, the command is basically called NLsolve. Inside parentheses, there are 2 parameters that you need to supply to the command. The first one is the name of the function, which is f in this case. Then after comma, you need to put initial guess. Since there are 6 variables, you need to put 6 initial guess values. So let's put into brackets so that it is all sent together at the same time. So the first one is M1. We know that according to this problem, the mass flow rate, the entering mass flow rate stream is 100 kilogram per hour. So the value of M1, M2, M3 is supposed to be around this value. So if I put initial guess to be 50 for M1, 60 for M2, 40 for M3, just wild number that I come up of my mind. Then for X, which is mass fraction, we know that mass fraction cannot exceed 1 and should be greater than 0. So if I put the number to be 0.5, 0.5, and 0.5 as our initial guess, all these 6 numbers here will be sent to the function to calculate the error. And then the function would return the number of error back and forth until the error will be adjusted until it gets 0. And that will be the answer for our system of the equations. So if you hit 1 by hitting Control Enter or Shift Enter, in this case, if I hit Shift Enter, no new cell will appear, and this command will be executed only. Okay. The result from the calculation would appear on top of the cell. In this case, everything after calculation will be written here. For instance, this is the starting point. It is initial gas as we enter. Then it has been calculated 2 times, back and forth 2 times. And then eventually the value of the function reaches lower than 10 to the minus 8. That means the value is converged to some data, to some number. And those numbers are reported here as 0. Okay? If you move to the right hand side, you see all the numbers. All right? All these data are calculated. If you want to assign all of these data to a variable, let's call this one solve. You can just say that everything calculated on the right hand side is equal to, or it will be assigned to the variable called solve. Then hit Shift Enter again to re-execute the command. Now you see that solve will equal to everything here. Okay? The good thing about assigning the calculation to the variable is that you can call, let's say, 0, which is here. This is properties or parameters of this variable. So variable is named solve. Parameter is 0. If you hit Enter or Shift Enter, this number will be assigned to this variable. Okay? So that means if you are interested in bringing more fraction x1 to do the calculation later on, you can assign this one to another variable. Let's say x1a equal to solve.0 number 4. There's 6 variables within the variable name here. We are interested in this number, which is the 4th element. Okay, this is the 4th element. So I put 4 in the square bracket. If I hit Shift Enter, you see that this number will be assigned to the new name x1a. And then you can do the calculation as well. For instance, you can multiply by, let's say, 100. Then the calculation can be done. Okay? So you can see that this kind of system of equations can be solved simultaneously with ease. And in chemical engineering calculation, we have this kind of system of equations quite often. You have system of energy and mass balance that you can solve together. And this is the way that we can do it quickly, conveniently. Okay. Another thing that I like to point out is that this NLsolve relies on initial gas. If I just want to show you the effects of this initial gas, let me recreate another function. So if I have a system of equations, for instance, b equal to a squared plus 1 and a minus b equal to minus 2. Okay, 2 equations, 2 unknowns. It should give you exact solution. Okay, and I'm going to repeat the process here. So we have 2 variables, so we need to define a function using command function. Let me call this function g. And the name of variable that will be sent back and forth from the Julia to come to the function, let me call this y. Okay, hit enter to get new line. The function or the equation is supposed to be within the bracket, so hit the bracket. Okay, the right hand bracket would appear automatically. So let's enter the function or the equation. As I said, the equations must be rearranged so that the left-hand side is equal to 0. So if I rearrange the equation, I will get b subtracted by ax squared minus 1 or subtracted by a squared plus 1 equal to 0. While the other equation, you get a minus b plus 2 equal to 0. Okay, and this part will be entered in the function command. So let's put it in. This is square. Again, I put 1.0 just to tell the program that this is the real number. When I finish, I put comma just to say that this is the end of the first equation. Just hit enter for clarity of my code. Then the second equation can be written a minus b plus 2.0. Okay, 2 equations already. Then I can put n here just to say that this is the end of my function. But before we doing that, we need to let the program know that the actual name of the variable that can be sent from function back to Julia engine is y. So we need to introduce that a is y number 1 and b is y number 2. Okay. Then hit shift or control enter just to get the new cell, and then you can enter NLsolve. If you want to assign this into another variable called solve, let me call this one solution number 2 equal to NLsolve. Inside you need 2 things. First is the name of the function containing the all equations. This is g in this case. Then initial value. We have 2 variables. Put 2 initial value within the square bracket. Okay. So if I put the initial value to be 1.0 and 1.0 and execute the command, I will get the 0 value. Let's say solve2.0. Execute the command. This is the answer for A, 1.618, and B, 3.618. Okay. Now let me show you that if I recalculate it, assign it to another variable called solve3 using the same command, NLsolve, same function, just different initial guess. Now if I put 0 and 0 as initial guess and execute the command, solve number 3.0, which is the answer, is completely different than solve number 2. So you can see that the initial guess really matters in this case. Why is it the case? So let me switch to this chart, and if I draw a chart for A and B, you see that the first equation is parabolic graph, right? And the second equation is basically linear. So there are 2 answers for this system of equations. So if you start with 1, 1, which is around here, 1 and 1 as initial guess, the program would run and find the solution as close as possible to initial guess. So it's run to this value, 1.618 and 3.618, which is the first answer. However, if you start initial guess at 0 and 0, it will go this way and give you minus 0.618 and 1.38 as the answer. Okay, so you have to be very careful to provide proper initial guess for this nonlinear solver. Otherwise, the answer that you will get might not be the correct answer. Okay, so hopefully you'll get some idea how useful this Julia programming would be, especially to solve chemical engineering problems. And I'm going to show you more later on in next video. Have fun.